All right, so example 3 here asks us, is there a relationship between the lengths of segment AB and segment AC in triangle ABC? So essentially what we're going to try and do is we're going to try and prove that the hypotenuse is equal to the square root of 2 times the leg. So given that we have a triangle, so they gave us a 90 degree and a 45, we know that the three angles of a triangle add up to 180, so 180 minus 90 minus 45. We know this other angle here is also going to be 45 degrees. So we have a 45, 45, 90 triangle, and we're going to try and prove that the hypotenuse here, AB, is going to be equal to the square root of 2 times the leg, which is AC. One of the legs is AC. Right? So the first thing we want to do, just like we did in example 1, is we want to draw in an altitude. Altitude. Okay. Since this is an isosceles triangle, we know that if we draw in an altitude, or it's going to be a perpendicular bisector. So if you draw in an altitude in an isosceles triangle, right, it's isosceles because 45 and 45, so AC and ABC are the same length. So drawing an altitude on an isosceles triangle makes this a perpendicular bisector. So if we call this point D, we know here that DB is going to be congruent to AD. Right, and that's going to be important later on. Right, so we have three triangles there, three right triangles. We don't need to use all three of them. We're just going to use the big one, and we're going to use the one at the top. So let's draw them separately. So the big one here is triangle ABC. We have a right angle and then two 45-degree angles. Right, and then in red, we can do the one at the top. So that's going to be triangle ACD. AD. That's also going to be a 45, 45, 90 triangle. We know angle A is 45 degrees. And again, three angles of a triangle. 180 minus 90 minus 45 gives us 45. But we didn't need all three angles. We only need two pairs of angles to show that the triangles are similar. So we can say that triangle ABC is similar to triangle ACD by angle-angle similarity. So triangle ABC similar to triangle ACD. That's by angle-angle similarity. Since the triangles are similar, we know that their sides are proportional. So we can set up a proportion here. We're trying to compare the lengths of AB and AC. And I notice AC is part of both triangles, so we're probably going to want to use that piece of both triangles. So let's start with the hypotenuses. AB is going to relate to AC here. So we'll do AB over AC. Okay, and then we can do AC over AD. Triangles are similar by angle-angle, so sides are proportional. So we're doing AB over AC equals AC over AD. We can cross multiply this. So AB times AD, that's just going to stay AB times AD. And then AC times AC is going to give us AC squared. So we want to relate AB to AC. So the problem is we have an AD in there. But we can relate AD to AB because we know AD is going to be half of AB. Since AD is congruent to BD, because our altitude was a perpendicular bisector, we know that AD is going to be half of AB. So that piece AD is half of AB. So we can do AB times a half of AD. Okay, well, yeah, it was AC squared. See how much room I have. Okay, so I'm just going to bring the 1/2 out front. I'm sorry, 1/2 of AB, not AD. Right, the whole point is we're getting rid of the AB. Right, so AD here is half of the whole thing, which is AB. So AD is half of AB. Okay, so if we multiply this together now, we have 1/2 times AB squared equals AC squared, right? To get rid of the half, because we don't want to deal with fractions, we can multiply both sides by 2. So if we multiply both sides by 2, we're going to end up with AB squared. Put an arrow here. So we're going to end up with AB squared equals 2 times AC squared. And if we notice, we're trying to get AB by itself. So to get rid of the square here, we got to take the square root of both sides. So we're going to take the square root of both sides. So square root of AB squared is simply AB. Really the absolute value of AB. AB equals, and then square root of 2, and the square root of AC squared is AC. We end up with AB here equals square root of 2 times AC, what we were trying to prove. So just to recap here, we had a 45, 45, 90 triangle. We're trying to show that the hypotenuse is the square root of 2 times the leg. And so we drew an altitude. Since the 45, 45, 90 triangle is an isosceles triangle, it's a right isosceles triangle. Our altitude is going to be a perpendicular bisector. Right, so AD and DB are the same. And then we redrew the big triangle and then the top triangle. And those triangles are similar by angle similarity, so we set up proportions. So AB over AC and AC over AD. We cross multiplied. And then we didn't want AD in there, so we substituted in half AB, because AD is half of AB since it was a perpendicular bisector. So then you get 1/2 AB squared. We multiplied both sides by 2 to get rid of the fraction. And then we took the square root of both sides.